So today's lecture is mostly about sequent calculus. And the notion of verification. But before I get there, I want to talk about one of the exercises that I mentioned to you, not the other, because I don't want to spend too much time, but I might come back to that in the problem session this afternoon. Okay. So you may recall I asked you to think about circle A by generalizing the judgment to say that A is true at time t, and then circle is true at time t if A is true at time t plus 1. That's our definition since we're verificationists, right? That should be the introduction rule because it's our definition of the connectives. Okay, does that make sense? Any questions or doubts about that? Yep. Yeah. Okay, if I were a pragmatist, then I would define it like this. Well, forget about the proof terms here. If circle true at time t, then A must be true at time t plus 1. I would define it like that. And then from that, I would deduce, well, if this is the way that it's defined, this is the way I can use it, then I should be able to introduce circle A again. So I would derive the introduction rule from the elimination. As a verificationist, I say, this is my definition of circle A. This is when I can derive it. And then if I can derive it, then what that essentially means that if M is of type circle A at time t, then I should be able to conclude that M has type A at time t plus 1. Okay? Yeah. No, essentially that's what it comes down to. If you define your connective by the elimination rules and you figure out what the introduction rules should be, or you start with the introduction rules, you figure out what the elimination rules will be, and you have to apply tests in both cases. And if all the tests pass, then the verificationist and pragmatist agree. Okay? Then we have harmony, right? Okay? Yep?
So I heard that in categories from Peter Hancock, it worked out a pragmatist mini explanation for logic, and then it's the jam. Do you know what went wrong?
Nope. It might be that there's issues when you get to type theory, when you have dependent types. So I don't know the exact story here. For the logic we're talking about here, it works perfectly. Okay. I suspect it might have to do with inductive types. Okay, so this seems pretty simple, right? Almost embarrassingly simple, right? You can check the reduction rule. I read the proof terms here. I say next of M is true of type has type circle A at time t if M has type A at time t plus 1. And then I have the opposite. If M has type circle A at time t, then at the previous stage, then prev of M has type A at type t plus 1. So it allows me, next and prev allow me to go between the two time stages. Okay? Okay, these are just names, but that's what they are. So then what's our reduction rule? What's our reduction rule? Which comes from checking what? Okay, remember back to, just yesterday. Okay. So what do we have to check? Someone, anyone? Local soundness, of course. So we want the elimination rule to sound with respect to the introduction. We need to show that any way to introduce the connective followed by any way to eliminate it can actually be reduced. Okay. So what does this correspond to here? Well, if we introduce it and then eliminate it, we get back what we started with, namely A at t plus 1. So it should be okay, right? Because we already have evidence of that. Everybody believe this by now? Or do I have to write it out? Make sense? And on the proof terms, what is the corresponding reduction rule? What is the reduction rule when you write it down on the proof terms? Prev of next of m reduces to m. Okay, does that make sense? Because when we have first the introduction and then the elimination, the prev is going to be outside of this next. And so it's going to, the previous of next of m gets it to m. Okay? All right. By the way, what time does m live? If we record with each term, what time does it live at? What time does m live at? T plus 1. Okay? So what's interesting is the reduction rule that gives you a term that lives at time t plus 1. Now reduction to preserve time. So this whole term on the left-hand side also lives at time t plus 1. And that's true because prev of next of m is of type A at time t plus 1. Is there anything else to say here? Do we have any terms at time t? Inside of prev, that term here, that lives at time t. Okay, does that make sense? Because the prev gets us down from t plus 1 to time t, then we take next, but the whole thing is, of course, at time t plus 1. It works out because next takes a term from time t plus 1 to 1 of time t. Okay? Doubts, questions? Okay, pretty straightforward, right? Okay. There was some concern about whether we should be able to prove this or not. Circle A or B implies circle A or circle B. Okay. So if you write the elimination rule like this, okay, so if A or B is true as time t, then A at time t, and then from A at time t we can prove C, and from B at time t we can prove C, then we're allowed to conclude C. And all this happens at the same time. Then at least with this rule, we won't directly be able to prove that. Okay? So here we introduce this assumption, circle A at A or B at time t, we call that x. Then here we can apply the circle elimination rule. And we know A or B is true at time t plus 1. Okay? And we have to prove that circle A or circle B is true at time t. Are you doing okay here? I've just played through the rules up to this point. Okay? And now I would want to distinguish cases on A or B, right? Because I know that I have A or B. But the problem is I can't apply this rule, right? I can't apply this rule because the assumption that what I know here, A or B, that I like to apply or elimination, is true at time t plus 1. What I'd like to conclude is true at time t. So applying the or elimination rule is like look into the future, right? It would be like flipping, somebody flips a coin tomorrow and making a decision based on that coin flip right now, today, at time t. Okay, so I would get stuck in this proof, at least if I go this way. Okay, now I'm suspicious about this. Okay, so I'm not completely satisfied about this, but at least from what I have on the board, it looks like we're okay. We won't be able to prove this. Okay, anybody see that? We don't have a proof that you can't do it, but at least with our strategy, by using introduction rules from below and elimination rules from above, right, we wouldn't be able to prove that. So there's hope that we would be able that this thing which we don't believe should be true can be proven. You okay on that? Okay. Okay, so now what is it? This all seems all very trivial, just a very simple idea to introduce circle and just following your nose with everything. So what does it actually give you? Okay? So let's think about that. So over here, I'm going to start a very small example, and I'm going to just throw in other types in order to give this example. Okay, so I'm going to define a power function, and it's going to have an exponent n and a base b. And for reasons of my own, I'm going to write it like this. Okay, oops, sorry. Okay, so b to the 0th power should give you 1. So I would write over here what the power function is. Power has type int, arrow int, arrow int. Okay? Okay, anyone believe this makes sense? Power 0. So this here is the base b, and this is the exponent. So b to the 0 should be 1. Okay? And I'm also going to write that the power function apply to a positive natural number. Okay, so what should it be? Okay, it's going to be lambda b. It's going to be a function from in to in. What does it do? B times power of n, not quite. Power of n gives me a function and apply to b. Okay? Everybody okay with this function? Okay, so what happens if I do power of 2 of the argument 2? This reduces to, what happens? Okay, I get lambda b, b times power of, 2 minus 1, applied to b, right? So I just substitute the argument in here, and maybe this n will be just 2 minus 1, okay? And so at that point, if I evaluate terms in a functional language, I would stop because I come to lambda. When I come to lambda, I usually give up evaluation. I return the function, right? So that's, I haven't discussed this explicitly, but that's the way both lazy and eager functional languages work, okay? So if I say power of 2, I stop after one step, essentially, with a closure, if you will, okay, in a functional language, okay? Nothing much going on, okay? So it would be nice if we could somehow play this whole power recursion through, okay, and not actually just do one step, but unwind the whole recursion to get something like, what I'd like to get is something like lambda b, b times 1. So is there some way we can arrange that a power function applied to number 2 gives you this answer instead of something like that, okay? See what I'm trying to get at. If you can do that, the process to go from here to here is called partial evaluation. Okay? I partially evaluate the computation based on information that I have to generate what's called a residual program that takes into account this information. Okay? Now, if you just do functional programming, you don't really get partial evaluation. You just get one step and you build a closure. Okay, so now the punchline will be that if I want a type system for partial evaluation, okay, then I should use temporal logic. Okay, and in temporal logic, I can write a program such that power of 2 will give me this result. Okay, so it gives you a very efficient piece of code that is very hard to achieve in ordinary functional programming without partial evaluation. Okay. Okay, do you see where I'm trying to go here? You might not know how to get there, but you kind of, okay. So how do we actually get there? So what we're going to do first is we're going to rewrite our type. Okay, so the way we're going to rewrite it is we say the power function has type. It takes an integer, and then at the next step, I want to get a function from integers to integers. Okay? So now I'm explicitly saying in the type, the power function takes an integer argument, and then it generates me a function from integers to integers that I can evaluate at a future time. And what this is going to be, this is the residual piece of code that I want to return. Okay? So I'm not just returning a function, but I'm actually returning something like this that can be evaluated in the future. So I'm saying explicitly there's 2 stages of computation. Stage 0 where I give an integer, and then stage 1 where I get back a function, which is my residual function. Okay? So how could I write this in my language? So I would say power of 0. Okay, how do I get something of circle type? Next. Okay, so power of 0 is next. Okay, and what is the code that I want to return at the next step, which has type int arrow int? Lambda b dot 1. Everybody agree on that? Right? Because the function that I want to get out, if I take power of 0, is lambda b dot 1, right? The constant function 1, no matter what the argument is. And I'm just going to underline the stuff that happened at stage 2. So at this point, we'll just have two stages, stage 0 and stage 1. Okay? So whatever happens at stage 1, I'm going to underline. Okay? So that's kind of code that I'm generating, not code that I'm evaluating. Okay? All right. So the interesting part is going to be power of n plus 1. Okay, so what is power of n plus 1? So it's going to be a circle, so we're going to do next. Okay, it's going to be lambda b, some function. And now what do we want to put in the body of that function? So I can't just say power of n applied to b. Why not? It's not at the right time, right? Power of n would be at time 0, but here I'm at time 1. Okay, so first of all, how about the b times? Is that at the right time? Because this variable b is at time 1, right? And the outside term is at time 0. Okay, you see that? That's a variable at time 1. So I'm going to say b times, and this is all going to be underlined, right? I'm okay with that. But I can't write power of n applied to b here. So what do I write instead? Okay, I write at the previous time, I take power of n. Okay, so now I have to be lucky, okay, or prepared. Okay, power of n, what's the type of that? Circle int, arrow int. Great. That's good because I want to take prev of that, right? And I can take prev of something which has type circle. So good. So this all happens at time 0. I'm not quite done yet. This application to b, at what time does that happen? At time 1. So that's okay, so I'll just underline that like that. Okay, does that piece of code make sense? Okay. So let's compute it over here just to see what actually happens. So if I do power of 2, okay. Okay, so this reduces to, well, the second case kicks in. Okay, so I get next. Okay, so now do I actually evaluate the right-hand side? The way I evaluate the right-hand side, when I come to a next, I'm going to go underneath the next. I'm going to traverse my term. And I'm hunting for prevs, because if I see next and I'm come to a prev, then I actually have to evaluate this now, because what's ever underneath the prev is going to be at time 0. You see why I'm doing this? Because I have to evaluate this because at time 0, so I'm obligated to do this now. So I'm going to go through the term. Okay, time 1, nothing happens, nothing happens. Okay, I see the prev, and now I have to evaluate that power of n. So I get next of lambda b times. Okay, that's going to be underlined, and now I'm going to call prev of power of n, which is 1 in this case, okay, and the result applied to b. All right, so I'm not done with this yet, so I have to reduce this further. Where do I reduce? Can I reduce this next? No, there's nothing to do. The prev I can't reduce, I have to reduce power of 1. It's at time 0, so I'm not going to, I have to reduce it, right? Time 0, I have to do everything. Okay, so I get next of lambda b times prev of power of 1. What does it actually become? Okay, so I have to do this again. So it becomes, okay, I'm going to run out of space, so put it here. Okay, so it's next of lambda b times, at the previous step, power of 1 becomes, maybe somebody can tell me, next of lambda b prime, just to make it different, b prime times previous of power of 0. and then apply to B prime. And this is going to be time 2, and then close it up like that. Okay? Everybody with me? Did I do the right substitution here? Okay, where? Like here somewhere? B, and that's underlined, right? Okay, I'll try to write larger. Okay, so now, what can I reduce next? At time 0? I can do that. There's another place where I can reduce. I have prev applied to next, right? Prev applied to next reduces to m. Okay, so I get next of lambda b times. Okay, so when I reduce that, what do I get? Well, I'll just plug in that term right here, lambda b prime times, and that's all underlined. Okay, and then here I still have prev of power of 0. This is applied to b prime, and then somewhere something is applied to b. Where is that? There? Okay, like that. Okay, so that's what I get. Am I done? No, I'm not done yet. The only thing I'm going to reduce at this point is power of 0. That's at time 0, so I have to do that. I get next of lambda b underlined times lambda b prime times, this is all underlined, and power of 0 becomes, what does power of 0 become? Next, lambda b dot 1, okay, and then this is applied to b prime, and the whole thing's applied to b, and that's all underlined. Okay, am I still doing okay here? Okay, so then this becomes next of, okay, lambda b times lambda b prime times, prev of next becomes what? Lambda b dot 1, and then that's applied to b prime, and then the whole thing's applied to b again. Okay, so probably, maybe this should be a double prime here. One more close, okay, which probably was missing already here. Okay. All right, so that's what I get, and this is all now underlined. So now I'm done, right? I've computed all the stage 0 redices, all the reductions, and I'm done with next, and this is my residual program. So there's no recursion in this program, so I've unfolded that. So you can do some beta reductions if you want. You can substitute this b for the b prime, and you can substitute this b prime for the b double prime. If you do those reductions, you get lambda b times 1. Okay. If you don't do the reduction, you get this thing which is there. Okay. So we haven't quite reached our goal. We haven't quite gotten this. Okay. We haven't gotten lambda b times 1. But we've gotten pretty close because we have unfolded all the recursion and get a residual program that's pretty similar to what we wanted to get. Okay. Now, there's a different program one can write for power, which I'm not going to take the time to do because I want to actually get through other lecture material, which has the same type, but which gives you exactly this. So it's slightly more complicated than when I wrote on the board. Okay. And that's your homework. Okay. Okay, rewrite the power function such that doing the stage 0 evaluation gives you next of this residual code. Okay. And now how does computation proceed in general in this stage language, in this partial evaluation language? Okay. It's actually pretty straightforward. What we do is like this. We start with an m, and let's say, for the sake of argument, we have 2 stages. Okay. What we do is we reduce this at stage 0 to something which has the type next of some residual program n, and n is going to be at time 1. Okay? So at that point, I can strip off the next step I want, and I can do the next step of computation. I can compute n-type circle A. We reduce that. Now we're back to time 0, okay, because we stripped off the next. We could formulate it differently. We could start evaluating time 1, but we can also do it this way. We get next of, okay, p, where p is at time 1 again, and then we can take p of type A. We can evaluate this at time 0 to some final value v. Okay? So each time corresponds to sort of one global phase of computation where we reduce everything at time 0 in our original typing, then everything in time 1, then everything in time 2, and so on to get a final answer. Okay? And that's partial evaluation. Okay? And it wasn't realized for a long time that this is just arises from a Curry-Howard interpretation of temporal logic with this one simple thing, circle of A. Okay? So the circle of A, which is almost trivial if you write it down, there's 2 rules, and you could, almost everybody here, I think, who tried it got it right. And out comes a really interesting mode of computation, namely partial evaluation. And there were dozens and dozens of papers written about this before with all kinds of complicated ways of figuring out which things you can underline and which things you cannot underline and so on. And these are all very systematically just unified by this idea that, well, we just have a next time operator in our type system. Okay? So this is an example of the power of starting from the logic and using the logic in order to actually arrive at something computationally interesting. Okay? And both of these things existed before, just like in the Curry-Howard isomorphism, right? We had intuitionistic logic, we had the lambda calculus, and people didn't realize that they were the same thing. And then Howard in '69 realized, hey, those are the same thing. That's an extremely powerful observation, okay? Because it means intuitionistic logic and the lambda calculus, the type lambda calculus, according to Church, are the same thing. So we can now develop a full type theory to reason about computations. So what one of my students, Rowan Davies, realized in '96 or '95 when he worked on this first is that there's partial evaluation, there's temporal logic, they are the same thing, okay? And everything becomes much cleaner, much simpler, much more well understood than before. And now, for example, we can have a dependent type theory that does partial evaluation. Before, people had no idea how to reason, for example, about stage code. With this, we're just logic, it's just temporal logic, right? You know how to do it now, okay? Okay, I think at least one of you came extremely close to what I'm showing on the board, but you didn't know the keyword partial evaluation, okay? But he essentially understood what was going on here, and I'm just putting it in a setting where you can actually really see what's happening. Okay, are there questions on this? Okay, and you should realize this is not an isolated instance, right? Whenever you realize that some computation phenomenon people have been thinking about and the logic are the same thing, that's a great discovery, because now you realize what the programming language construct really should be, what there should have been. A lot of partial evaluation work, people spent years trying to figure this out. Now we know definitely what it should be. Okay. All right. And in the last 2 lectures, when I talk about linear logic, I'm hoping to induce in you the same sense of accomplishment, okay? That to understand concurrent computation, we know what it is. It's related to linear logic. We know what the primitives should be. We know how to type it, and we also should know how you can develop a type theory to reason about concurrency, okay? And this is a much more recent discovery. This was '96. The stuff I'm talking about in the last 2 lectures is going to be 2010. But it's the same thing. People have thought about concurrency for a long time and trying to figure out how to have type system for the pi calculus and how to have a good language that does it and be able to reason about that. And on the other side, people were doing linear logic for a long time. They had a vague idea, it had something to do with concurrent computation, but really not very crisp. In 2010, Louis Kirish and I figured out that, oh, they are the same thing, okay? So that's just a preview, okay? But today, I need more background, and so I'm going to talk about sequence calculus and verifications. Are there questions on this before I move on? Yep.
Why is it that, so in that original example, you wouldn't reduce under lambdas, but with the temporal logic example, you did reduce under lambdas, within the next, and it was the time was 0?
Yeah, so when you define the operational semantics or reduction for this, you have to look under lambdas because you have to reduce everything that's at, you don't reduce under level 0 lambdas, okay? So that's the same. But when you come to a next, you have to evaluate under the next, and you have to hunt around for things that you're supposed to do. So if there was a lambda at stage 0, you wouldn't go underneath of that, okay? So it's only in a term at a future time that you have to analyze to extract the pieces from a previous time. Yeah?
Some things that the logic doesn't tell you, but that you have to figure out on your own when you try to figure out how to evaluate the term?
Correct. So it's similar to the logic doesn't tell you, like I said yesterday, whether its language should be called by name or called by value or called by push value, whatever, okay? But there's a strong intuition that the times should be times at which you reduce or that you do it in stages. That's why it was designed. And so when you follow that lead, then you end up with that. Okay. Other questions? You had a question back there? Okay. All right, so let's move on. So, okay, so at the beginning I made a very important statement, and I'm going to rewrite it because this is something where all of this leads back to, okay? And the statement is that this is a Martin Leff 83, but actually I think it goes back to Dummett. And by the way, I posted on Piazza the sources for these original papers if you want to look what people actually wrote way back when they first discovered these things, okay? So the meaning of a proposition is determined by what counts as a verification of it. Okay, and I asked you to postpone your disbelief, okay, but what I did is I substituted the word proof for the word verification. And today I'm telling you that this was wrong. I shouldn't have done that, okay? Pedagogically it might have been a good thing, but actually it's not good, okay? And the reason is as follows. If you want to understand the meaning of a proposition by the space of all of its proofs, okay, then you have the following problem. Let's say implication elimination looks like this. If A implies B is true, and A is true, then B is true. Okay? So for example, if you want to understand the meaning of a proposition, or you want to understand all of its proofs, then you also would have to understand the meaning of this proposition here already before that, and this proposition already here before that. Because these are potentially, well, A is potentially completely unrelated to B, and A implies B is much larger than what you're trying to understand. So our definition, according putting the word proof here, is not really well founded, right? It's kind of circular. So to understand the proofs of B, we need to understand the proofs of A implies B. Well, presumably to understand the proofs of A implies B, we eventually need to understand the proofs of B, which is what it's trying to explain. So see our definition, okay, I pulled a fast one on you, okay. So we can't do that exactly as it's stated here. We can't look at the set of all proofs and say all proofs taken together is my meaning of the proposition, okay. So we want our meaning definition to be compositional. So what that means, for example, is the meaning of A and B should be determined from the meaning of the components, the meaning of A and the meaning of B. Or the meaning of A implies B should be composed of the meanings of A and B, and not something else that may be around there, right? So we want our meaning explanation to be compositional. If I say proof, then it wouldn't be compositional because of that. So how do I make it compositional? Okay, so that's the next key idea. Okay, so when I explained to you end introduction, why did you believe that explanation? Because that was very convincing?
Drawing pictures and presumably you can do reduction on like the size of the picture.
Yes, okay. it's the size of the picture, but more importantly, I said something like, so to prove A and B, you have to prove A and you have to prove B. Okay, and in that rule, we're actually breaking down the conjunction into its pieces, right? So this is something smaller, okay? So now the notion of a verification, which is a restriction of the notion of a proof, is going to force this decomposition. So a verification of A and B is going to consist of a verification of A and a verification of B, okay? So I'm going to write verifications by up arrows. This is a new judgment about propositions. So previously, the proof is connected to the notion of truth. Okay, A is true. And here's, I'm going to write A has a verification. Okay. Now I'm writing up arrow because I'm thinking about the introduction rules being used from the conclusion to construct the proof of that. I'm going to have to construct proof of that. So I'm working my way upwards as I'm constructing proofs. Okay, makes sense? Okay? So in particular, I will enforce that this is not going to work. A verification of B is not going to consist of verification of A implies B together verification of A. It's very important to rule that out because that would violate our principle that a verification of a proposition only depends on the verifications of its pieces. Okay? Are we clear so far? Okay. So for example, what is verification of A or B? Verification of A. And there's another way to do it. Verification of B. Okay. What's the verification of truth? No premise. Okay. That counts as verification of truth. What else do we have? Implication. What's the verification of A implies B? Okay, so it has to be verification of B, A, blah, X, implication, introduction, X. Okay, so at this point I'm getting into trouble. Okay, why am I getting into trouble here? Right, I have no way of checking that A. I can't build a verification of A. But what did I tell you about the elimination rules? Tell you some very important facts about the elimination rules. I gave you some very practical advice on how to do your proofs. Right, you use, when you have something that you can use, that you know, then you work downwards by using elimination rules, right? Okay? So A is something you can use. Okay, so I'm going to read the down arrow for that. Okay? All right. So, okay, everybody remember this is what we don't want. Okay? All right. So let's do a conjunction. How do I use a conjunction? How can I use a conjunction going downwards? I can then use A, and I have a conjunction. I can then use B. Okay. How do I use a disjunction, A or B? If I derive that somehow and I know it, how do I use that knowledge? Yeah? Oops. Okay. Yeah, that would have brought our program to its knees right away. Okay. All right. How do I use A or B? Okay, I assume A. Okay, any assumption is going to be down. I can use that assumption. Or elimination, X, Y. I try to prove C. And now here I get C. And I'm going to just arbitrarily say, without much argument here, that, okay, to get a verification of C, I can use the assumption, A or B, which I know already, and I use it, okay, by be able to use A here in this subproof and B here in that subproof. Okay? How can I use falsehood? Okay, verification of C. It's a zero error case of that disjunction without any components, so no branches to consider. And so the question is, how do I use an implication? Okay, well, remember the rule, right? We have to prove A, and then we have to conclude B. Now we just have to put right arrows on that. Okay? What arrow in B? Up? No, we didn't want that, right? So no, if I know A implies B, then I know B if I can find a verification of A. Okay. Okay, so if I know A implies B, then I'm allowed to conclude B and use it in the rest of my proof, but I have to supply some verification of A. Okay, so there is a switch direction. Yep.
How do you read the arrows? Would be like as a verification and down to
Down arrow B is something I can use to construct a verification, right? Something I'm allowed to use. Yeah. Okay, so what happens here in the implication introduction rule, okay, the B inherits the same direction. To construct a verification, I have to construct a verification of B using the assumption A, so that's down. And then implication elimination, the opposite happens. Okay, this arrow is going to be both down on both sides. This is what I can use, and this is what I can use below that. But this is going to be up arrow just because the arrow here kind of also gets flipped. We're here? Oh, here. Oh, that's an introduction rule. Okay. And introduction rules construct verifications. I just don't happen to have any premises. Right? And I don't have any way to use top. There's no elimination rule, so there's no down arrow version of it. Here I only have a down arrow version of it, because there's no way to construct a verification of falsehood. Yeah?
So this seems a lot like type checking to me. Would it be an okay analogy to keep in your mind as the up arrow is check the proof of A, whereas the down arrow is infer the proof of A?
Yes. Yep.
So why is it that, I guess I'm trying to understand why the arrows can go either way on the bottom of the suggestion.
Either way on the bottom of. I'm not sure I understand the question. What we're going to do systematically, forget about the implication, is that we're going to annotate all the rules. The introduction rules construct a proof from the bottom up, the elimination rule from the top down. Okay? And we force that by putting the arrows on the rules. Okay? And now I claim the following property. If we start with a theorem to be proven without any assumptions, if we have some theorem A and we try to construct a verification of it, then in the whole verification of A, we'll only ever have subformulas of A, which is what I wanted, right? I want my verification to consist only of subformulas of A, right? So why is that true? Let's check it. So here we only get subformulas of A and B, so that's obvious. Here we get subformulas. Well, there aren't any subformulas here. Here, we get a subformula here, and we also get another subformula we can use, okay? Now, when we can use something, we already know the thing on the top is going to be a subformula, right? Because the only thing I assume are going to be subformulas, what I would try to prove. We extract a piece of that, that's also going to be a subformula of my initial goal. Same thing here. Here, okay, A is going to be a subformula of A or B. B is going to be a subformula of A or B, okay? So the subproofs only consist of subformulas, okay? Here it's a little weird. I'm trying to prove C, so that's a subformula. This has to be a subformula of what I started with, and so therefore there's nothing here. Here, this is a subformula, sort of inductively. And then B is also a subformula because it occurs in this one here. And A is a subformula because it occurs in here, and we're going to construct a verification here, and that verification consists only of subformulas of that. Okay? It's a very sloppy inductive argument, but you can make it precise, right? So because we only use elimination rules only downwards and introduction rule only upwards, okay, the whole verification of some formula A that we start with, proposition A, is only going to consist of subformulas. Okay, does that make sense? So at least if you believe the system, then it should be the case that verification of A only uses the components of A. And that's really important because that's a well-founded meaning definition of the propositions. So that's why we really can say the meaning for propositions is not determined by all proofs, but just by the verifications. Okay? Yep?
How do you prove, for instance, A implies A? Or do you find verification of A implies A?
Yeah, very good. Excellent question, because you can't.
Yeah, you liken the rule like you can use A as a.
Right. Okay. You asked the question that I wanted to ask you guys, so that was a very neat preemptive strike. Okay. All right, so how do I prove A implies A? Okay, actually, let me try to prove A implies A implies A. Okay, so I do implication introduction, call the assumption A, X. Okay, but I want to construct a verification of it, so now I have to construct a verification of A implies A. Okay, I use implication introduction again, call this Y, A, Y, and this goes down, and A goes up, and oops, I'm stuck, right, which you very correctly noticed. Okay, so what rule is missing? I think you said it. Okay, so if I can use A, then that's sufficient to count as a verification of A. So this is the down, up roll, okay? And then I'm going to use that here. So an interesting fact, how many verifications are there, okay, of A implies A implies A? How many verifications are there? There's 2 verifications, right? Because I just went through systematically and constructed it, and my only choice, do I put X here or do I put Y here? Right? Oh, sorry, not there. This is definitely the down-up roll. The question is here if this is going to be X or Y. These are the only 2 things that I have. How many proofs are there of the statement? A implies A implies A. Infinitely many. Why is that? Well, I can always decide to prove A implies A implies A by proving that B implies that, and B for any B that's true, right? Then it follows by implication elimination that A implies A implies A, and B is arbitrary. All I need to know is I can prove it, right? Where there are infinitely many formulas I can prove, so there are infinitely many proofs of that, which is a whole lot, okay? But there's only 2 verifications of it. And you've just seen why, because I have explored all the possible alternatives, okay? So it's really important there's only 2 possible verifications of it, okay? All right, so that's verifications. Now what question arises? The question arises, how are verifications related to truth, right? So verifications are extremely important because, for example, I want to show my logic is consistent, okay? What does it mean to consistent? It means I cannot prove falsehood in it. Okay, so is there a proof of falsehood? Well, I don't know. There could be, because it's possible that with the right lemma, A implies falsehood in A, I conclude true. So that's possible. Okay, so there's possibly a proof of falsehood. I don't know how to get around that. But How many verifications are there of falsehood? How many verifications are there of falsehood? None there? Is there any other number? Yeah? 0? None, 0, zilch, zip. Okay, yeah? Right, but I'm talking about here verification from no assumptions. Yeah. Yes, if you assume falsehood, yeah, then you can get falsehood. But if you make no assumptions, how many verifications are there? Let's look at our rules. Which rule could we possibly apply? Just go through them one by one. Can we apply this one? Can we apply any elimination rule? No, because the conclusion, but possibly this one, right? But for this, we have to have A or B, which we don't. Okay. Yeah, the only thing we can do is the up-down rule, right? That's our only possibility. Right? Or we could have falsehood elimination. Okay. They look eerily similar. Okay. Okay, so now how we can proceed? How can we justify bottom-down arrow? Which rules allow us to do that? Okay, so let's look at the rules. Well, we don't have anything we can apply down arrow to. So we shouldn't be able to prove that because no rule should allow us to actually be applied. Okay, but it's not a very crisp argument, right, at this point. So when Gensen originally developed natural deduction, he came up against this problem. I mean, he didn't define the notion of a verification, but he came up against the problem that there's infinite many proofs, and so, but he really wanted to show that the logic was consistent. You couldn't derive falsehood in it. That was the key of what he really wanted to do. But with the inference rules that were given, you can't quite do it. And when you look at the natural deductions, even if you make the restriction to up and down arrows, it's a little bit fuzzy because you have to think, oh, the arrows are down there, the up arrows down there. It gets a little, tricky to work with. Okay, so what he did is he said, wouldn't it be nice if all inference steps went from the conclusion to the premise? Okay, so we're working always upwards, 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 instead of working from both directions. Okay, and that's where the sequent calculus comes from. So I'll show you the rules. Okay. All right, so what does a natural deduction look like? So a natural deduction now, actually I should say, maybe I should say verification. Okay. So a verification looks like this. So we work with introduction rules from below. Then we have this down-up rule. We have some assumptions up here, and you work downwards with the elimination rule to that. And they have to meet in the same formula in the middle. Right? They have to meet in the middle at a formula which is the same. And then because of the implication rule, implication elimination rule, that picture can kind of repeat sort of in a nested way. Okay, does that make sense? Okay, that's what it looks like. So forget about the nesting for the moment. So we have elimination rule downwards, introduction rule upwards, and they meet in the middle. Okay, so now to develop the sequent calculus, what I'm going to do is I'm going to turn the elimination rule upside down, so they go upwards also. Okay, and I'm going to establish some kind of a correspondence here to something like this. So I'm going to have up rules, and the so-called right rules are going to be related somehow to the introduction rules, and the so-called left rules are going to be related to the elimination rules, except going in the opposite direction, the inverses of the elimination rules. And instead of just saying, we're saying these things here, the sequent arrow, the right, and then here where they meet, we'll just call this identity, okay, instead of the up-down, okay. Because for these to meet, they have to be the same formula, and here also for the identity, the left and the right have to be identical, okay. So this is the picture. Now I'm going to write down all the rules based on what the picture tells us, okay. All right, so the easy one are the so-called right rules. So here's what they look like. So the basic Okay, so I should write it like this. So at any point in time, I have some propositions on the left of the arrow and one proposition on the right. Okay? And so these are usually called the antecedents. And this is called the succedent. The whole thing here is called the sequent. And this thing here is usually abbreviated just by the letter gamma. Okay? So I don't have to write dot, dot, dot all the time. So the things in gamma are the things that I have derived by going downwards, okay, by elimination rules. And the succedent is the thing that I'm trying to prove with an up arrow. So you should think about this as roughly as the correspondence would be assuming that I can use A1 through AN. I'm trying to construct a proof, a verification of C. So this picture is supposed to be translated into this form here, okay? But instead of working in both directions, I'm going to work always upwards. Okay, so that's the magic of the sequent calculus. And what happens when you do that is you can reason about it much more easily. You can do inductions over the structure of proofs and all this kind of stuff that you can do for natural induction, but it's tricky because the proofs are built in both directions. Okay. All right, so let's start with the identity rule. That's very easy. So if I have some assumptions and one of them happens to be A, then I'm allowed to conclude A. And that's the identity rule. Okay? All right, now the end introduction rule, can somebody suggest what that would correspond to? No, the up-down rule is this one. So that corresponds to the up-down rule because that's the place where they meet, and I translate that to identity. So the end introduction rule is going to look like this. So if from gamma A follows and from gamma B follows, then from gamma I get A and B. And this is going to be the right rule. And of course it looks exactly like the introduction rule, except that I have written down the things that I can use on the left-hand side. So using everything in gamma to prove A and B, I can use everything in gamma to prove A, use everything in gamma to prove B. Okay? And all the introduction rules have that kind of a flavor. Okay? So they just work the same way. So for example, from the assumptions I can prove A or B. If from the assumptions here I can prove A, from the assumptions I can prove A or B. If from the assumptions I can prove B. And so this is the first or right, and this is the second or right rule. Okay? Okay, does all that make sense? Okay? So, since we're on the right rules, what's the rule for the right rule for implication? Anybody have a suggestion? Yeah. Right. So gamma together with A proves B, right? And that's because when I use the implication rule here, okay, in the verification, I'm allowed to assume A, so it gets up here, which means that in the sequent it ends up on the left-hand side as something I can use. Okay? Everyone would believe that? Okay, so that's the right rule. So these right rules are very easy to construct, okay, because actually, what's the right rule for top? I think we're done with that. From gamma, I can prove top if, that's it. Okay, good. Our right rules are done. Okay, half the sequent calculus is done. Yep.
So for the order right rule, can you just speak a sentence again? I think I'm a little lost.
Okay. To prove a verification of A or B from the assumptions in gamma is a verification of B from the assumption in gamma. No, you don't know that. This is what you're trying to show. So the right-hand side is always the thing which you're trying to show, and the left-hand side are the things that you know. So you don't lose anything. Everything that you know, you still know. And to prove A or B, you have to prove B. Okay? So we always think about this as a proof search process as we're working our way upwards. Okay, other questions? No, so the ID rule is neither right nor left because it's not concerned with any connective. So sometimes we call it the structural rule, or sometimes it's called a judgmental rule. Okay, it's like this one, the up-down, which holds for arbitrary propositions. So it's sort of, it's not really, it's just sort of plumbing together the different judgments, up and down, right? That's why I like to call it judgmental rules, because it's about the connection between the up and down judgments, right? The verification and the use judgment. Yep.
Could you possibly provide a little bit of information for the last rule? So if we have gamma and A and we know B from that, how is it that we know A implies B rather than gamma?
Okay, so look at the introduction rule there. Okay, to prove A implies B, I have to prove B. But I'm allowed to assume A. And assuming A means to put it on the left-hand side because that's where assumptions are that you can use. Does that help?
Yeah, I mean, I understand what the rule's saying.
Yes, you don't have to use the assumption as people found out in the homework assignment. Yeah. Yeah. Okay. So you don't have to use the assumption, right? So you see that here, right? There's lots of assumptions that are not used. But it's okay not to use assumptions, not to use the assumptions. So gamma is an over-approximation. It's everything we could potentially use. And we can use it as often as we like. For example, here, we propagate into both sides because we can use it in both sides. Okay. Good. Thanks for the questions. Let's look at the left rule. So now the left rules are much trickier, okay? Because we have to turn them upside down. Okay, so let's try to think about it this way. If I have gamma, and I know A and B, and I'm trying to prove C, how can I use the conjunction? How can I use the conjunction?
Since we know gamma and we know A and we know B, and we're trying to prove C.
Right. So I could do that. If I know A and B, I know A and B together, and I know C. So that would be a fine left rule, because it's okay to break down the conjunction. But that's not exactly my program here. My exact program is to invert the elimination rules exactly, right? So if I invert the elimination rules exactly, what would I get? Just A. Right? And that would be the first left rule. That would be slightly unfortunate. Why? Well, I want B at some point. But the thing is that our assumptions should be monotonic in some sense. I should only be able to gain more information. I should never lose anything, right? Right. So I keep A and B, but I add A as something else that I can know. So when we have something we've derived, we can always keep it. We never lose it, right? Okay with that? And what's the second left rule? A and B, arrow C. Well, I keep A and B, and I add B. That proves C, and that's the second left rule for conjunction. Okay? Everybody on board with that rule also? Yes? Okay. What rule do we want next? Implication, maybe? All right. I'm in gamma and I know A implies B, and I'm trying to prove C. How do I do that? So this would be the implication left rule. How do I use the assumption A implies B? Now we have to look at the arrows there. I apply implication elimination, right? Okay. How do I apply implication elimination? Okay. I need a verification of A. How can I get a verification of A? Gamma arrow A. And once I have a verification of A, what can I use in my context? B. So I can take gamma and I add B to it and I prove C. Okay, except I made a mistake here, same mistake I made with conjunction. Right. So let's redo it. So I keep A implies B, and I try to prove A, and I keep A implies B, but I add B, and then I get C. Okay, so that's the left rule for implication. So these copies just say, okay, I can still use it if I want, everything is monotonic, but I have to prove A, I have to have a verification of A, and then I can use that to prove B. Okay? The or left rule, how do I use the knowledge that A or B while I'm trying to prove C? You can look at the thing over there, or you can just try to think about it in the abstract. How do I use A or B? Okay, so I have the two cases. I add A to gamma, okay, and I add B to gamma, and I have to be able to prove C in both cases, right? So if I know that, I have that proof obligation and I have this proof obligation. Make sense? By cases. It's the same thing I did in natural deduction, right? If I know A or B, so I can use that, I break it down into that proof of C and that proof of C, and then together it constructs the proof of C. So the three occurrences of C here are the three occurrences of C here. That's the assumption A, which is new over here. The assumption B is new over here. And A or B is still available in case I need it again. Okay? Okay with that rule? Yep. Yes. That's right. So here's my goal. I want to show that for any strategy, for any number of steps that construct the verification, I get a corresponding sequent calculus. Okay? If I dropped A or B here, then there would be some stupid strategy I can apply over there that I wouldn't be able to replicate over here. So because A is stronger than A or B, I really no longer need that. But that's an optimization. I want to be the correspondence to be as simple as possible. So I want everything to be monotonic. Okay. So that's the or left rule. But one thing you notice here, these rules are a lot more uniform than the natural deduction rules, right? In natural deduction, the elimination rules for AND are very clean and simple. The one for OR is very strange, right? Because you have to have that C formula lying around. But here they actually end up being the same thing because you always have the C on the right-hand side. So now all the rules look more similar than they did before. So that's one simplification that we get out of this. Are we missing some rules? Bottom, okay. What's the left rule for bottom? Okay. Anything else I have to write here? No, I don't have to do that because if I know a contradiction, then I conclude anything. I don't need anything else to prove. So this is something I can use. So that's exactly transcribing this rule. To get a verification of C, it's enough to be able to use bottom. So there's no premise here. I'm done when I have a contradiction on the left-hand side. Okay, so that's my sequent calculus. Yes?
So the IP rule, is that supposed to be A anywhere in gamma, or is it on the front of gamma?
Okay, excellent question. So because in natural deduction, I don't care how I write down the assumptions. You can permute these things to be anywhere in gamma. So you can always permute your assumptions. So I don't care about the order. Okay. So we usually think of gamma as being a multiset. You can have multiple occurrences of the same thing, but the order doesn't matter. Okay. Yeah? Yes, because one forms a judgment, the other one forms a proposition. So I can't say something like A double arrow B double arrow C, double arrow D. That wouldn't make sense, right? It has to be a formation of propositions, and the double arrow here forms a judgment with some assumptions on the left that you can use and a conclusion on the right that you have to prove. So that's the difference between the double arrow and the implication. Other questions? Yeah? Right. So, in fact, in many places you will see a turnstile written for that. Okay. So, there's another way to write this. Okay. And another way to write that is that A1, AN, turnstile C. Okay. And that's a way to write natural deduction. Okay, the only difference is that you write your assumptions on the left, but the rules still operate on the right. Okay, and so just to be able to distinguish between natural deduction and sequent calculus, I wrote the sequent arrow that way. Okay, whether you write this or the double arrow, you always have assumptions on the left and you have a conclusion on the right. But with this arrow, you would have an elimination rule that looks like if you have gamma and A and B, then from gamma you're allowed to conclude A, and that would be an elimination 1. In the sequent calculus, there's no such rule. Okay. Okay. More questions? Yeah? Yes. Right. So if you know this, then by using the implication right rule, you can always infer A1 implies that A2 implies C. Okay. You can always prove that if you know the sequence, if you know that. Yeah. Okay. So that's the sequent calculus. So now unfortunately I have only 5 minutes, okay? So I'm going to have to spill this over into next lecture. But, so what we want to prove now is essentially that, first of all, we want to prove that the notion of a verification is the same as a proof of a sequent calculus, that there is a kind of, you can go back and forth. So if you have a sequent calculus proof, you can get a verification. If you have a verification, you can get the sequent calculus proof, right? So that I'm okay to saying if I have a sequent calculus proof of something, then I have a verification of the right-hand side. Okay, so that's an important theorem to be proven. And the second theorem I want to prove is this all-important theorem is that A is true if and only if A has a verification. Okay, so that means whenever I do a proof and I use rules whichever way I want to, it's okay, because anything that I can prove with all of the rules used freely, I can also find a verification for. Okay, and that's really important because that basically says the proof rules that I wrote at the very beginning without the arrows are okay. There's nothing wrong with my proof system because anything I can prove, anything that's true according to the rules also has a verification. And so that means the meaning of a proposition is determined by counts of a verification of it is a valid program, is a good program. Okay. And these will turn out to be the global analogs of the local soundness and completeness theorems, right? So I can't prove them today, but I can show you how to do it next time. What I want to finish up today is uses of this, okay? Let's get rid of this here. Applications of it. So in the sequent calculus, on the right-hand side, we make explicit all the assumptions that we have. So how many sequent proofs are there of this? No proofs, right? Okay, so this can't be proven. So this means our logic is consistent. Okay, so that was the first corollary that Gensen had, I think, in his paper, that essentially if you can reduce all sequent proofs to that, then the logic is consistent. Okay? How about this? If I have no assumption, am I trying to prove A or B? What are the possibilities for that? So if I have a proof of A or B, then either I must have a proof of A or I must have a proof of B. Okay, and why is that? Well, you look at all the rules, and the only sequence rules with that conclusion, okay, with this, only rules that apply to the sequence are these two rules, this one and this one. No other rule applies. And if it's this one, then A is true, and if this one, then B is true. So therefore, if I can prove A or B, I can definitively prove either A or B. Okay? Make sense? Okay? Why is that so important? Well, if I have a proof of A or not A, okay, what would such a proof look like? Well, okay, it would have to be either a proof of A or a proof of A implies falsehood. But it couldn't be a proof of A because I don't know anything about A. So in particular, A could be falsehood, and then I wouldn't be able to prove that. Okay, so if I try to prove it by the one case, I will get stuck. So that can't be the case. So it must be that A, that. If I can prove that, then I can prove that. Well, how do I prove that? Well, there's only one rule applies. It means from A, I must be able to derive falsehood. Now, which rules apply here at this point? Is there a right rule for bottom? There better not be, because that means I could verify falsehood, which I can't. Is there a left rule for A? Well, I don't know what A is. This is supposed to hold for any proposition A, so there's no left rule for A. Okay? Okay, so I can't proceed here either. So I can prove A or not A in general. It's impossible to do so in intuitionistic logic. Yeah?
Why do you use the proof now and not the
Sloppiness. Okay, so if my theorems that I still have to prove hold, then just using the sequence calculus, I can prove all these consequences. Like if I can prove a disjunction, I must be able to prove either case. Or if I cannot prove A or not A in general in intuitionistic logic. Okay, so that's extremely powerful. Plus, all the rules now work bottom up. So when you try to construct the proofs that you had in the homework exercises, it's actually much easier because you just go upwards, upwards, upwards. You don't have to think, oh, do I go down, then here, how did they fit together, all this stuff. Okay, it's easier. So as a homework exercise, take your least favorite proof that you did so far, okay, and rewrite in sequence calculus. But I'm only give you one more thing. If you don't need an assumption anymore after you apply the rule, you don't have to write it, okay? This reduces the amount of paper you have to spend, okay? In the rule, it has to be there because we don't know when we're constructing proof bottom up if you're going to need it again. But you know because you know the proof. So if you don't need something, you can toss it away, okay? That's, by the way, it's called weakening, yeah? Yes, you still have a choice. Obviously, you always have a choice. And there's even better strategy than what I'm telling you now, okay? But at least you don't have to worry so much about the two-dimensional arrangements of the pieces of your proof, right? So please go through that with your least favorite proof, right? Or maybe the one that you couldn't even do, and try to see what this looks like in the sequence calculus. Okay, any more questions? Okay, so here's what I'm going to do next time. I want to have at least one example where we reason about our proof system rigorously. So I'm going to prove one of the theorems that are associated with this for you, okay? By which I mean I show you one case and I try to make you believe all the other ones, right? That's what I mean by proving, okay? And then I'm going to move on and discuss linear logic. Okay, now that we have the sequence calculus, it's much easier to introduce you to linear logic because it so turns out that it's easier to present from a sequence calculus perspective than natural reduction. And I'll also, well, okay, so that's for next time. Okay, any more questions or points of discussion? Yeah?
So, like, it's a programming language. Is this kind of like a normal form, or
Okay, excellent. I forgot to give you homework assignment. Okay, that'll teach you to ask questions. Okay. Okay. So what I want to do is the following. I want to do a proof term assignment to these things. The way I'm going to do that is certain terms are going to be evidence for that, and other terms are going to be the evidence for that. Okay? And I want you to write down, okay, what are the possible R's? And what are the possible N's? Okay? So please do that. Okay? So use the same terms that we had before. Pairs, projections, lambda abstractions, applications, left, in, right case, and so on. Okay? Invent something new if you have to. But otherwise, just annotate these rules and see what the language looks like, the language of programs, okay, that comes out of that. That language of programs would be the right one for the sequent calculus so far, okay? Because we developed it systematically from here to the sequent calculus, so that would be what you would write into the sequent calculus. Any more questions? If somebody took notes, they can post it on Piazza. I forget what I said. Don't exploit that, please. Yeah?
Are the elimination rules for R and bottom really supposed to be verification for C? Because if you go with the intuition for checking and inferring,
You mean here?
you're inferring. Yeah.
Right. So I can use that, and I break this down to be able to use A and B. So that part should be clear, right? I'm breaking down the use of A into A or B into uses of A and B. So that's the subformula property. And do this while I construct a verification of C. Okay. And so then that's why the rule looks like this. If you were doing this while you construct a possible use of C, what would that look like? Oh, that's a good homework. Okay. If we had another rule which said this with the red version, construct the corresponding sequent calculus rule to that. It's a reasonable question. Every time I've given this lecture to any audience, somebody's asked this question, so I'm really glad we got there this time. Yeah?
I'm still a little confused by that answer. Is my intuition about these verifications and these uses is that one of the verification is that when you treat the deduction tree as proof, then you have a canonical form. Right?
Okay.
And that doesn't look like a canonical form, it's like an elimination form.
Well, it turns out to be canonical.
Okay.
But you'll see that when you write down these things here. Yeah. Yeah? Okay, so it's true that if you can prove gamma arrow A, if you can prove this in the sequent calculus, if and only if you can prove this in natural deduction. Okay, so you get the same consequences. But if you're asking what is the structure of the proofs, they're very different. Of course, in the sequent calculus, you work always bottom up. In a natural deduction, you go back and forth. Okay, and so it turns out there's many many sequent calculus proofs which all correspond to the same natural deduction. Okay. Say that again? Yeah, you can prove the same things with both. But what Bob said in his first lecture is proofs matter. The structure of proofs matters. And the structure of proofs is very different in the two cases. And so that from our point of view, that really matters. So you could now go off and try to design a programming language for the sequent calculus, and nobody would want to program in it. Okay, but you could do so. In fact, Tomorrow we'll do so, or maybe in 2 days, okay? And maybe you'll see a different way. So, but we do it for the linear sequence calculus because this sequence calculus is not, in the intuitionistic case, natural reduction seems to be much easier to work with for reasons which are a little difficult to explain, but yeah. So you can prove the same things, but the structure of proofs is very different. And computation arises from the structure of proofs, so computation would be very different. Yeah. You should ask Zina that because she's also been working on that. Other points of discussion or questions? All right. Oh.
Do we have in the sequence calculus something like the harmony criteria?
Yes, excellent. Very good question. Yes, we do. And we'll see that tomorrow. Yeah. The question is whether there's a harmony criteria for the connectors in the sequence calculus, which is a really excellent question. And yes, there is, and we'll see it tomorrow. Okay.